Hey CW Apes, are you ready for part 3 of chapter 17, notes on air pollution? I bet you are. So hey, part 3 here of this video series, we're going to take a look at climate and topography, and we're going to eventually finish up with like advances that we're making to try to reduce air pollution overall. So first thing we got to talk about is climate and topography. So when you think about air pollution, aside from just putting stuff up in the air, climate and topography play an important role in literally like trapping that air pollution and potentially making things a whole lot worse. So when you think about climate and topography, the most important point that I can make regarding it is this idea of a temperature inversion. So normally, if you remember what you learned about convection cells, when you create warm air, it rises, eventually cooling in almost kind of like a mushroom shape and falling back to Earth. Like that's the normal order of things. And if there's pollution in that column of air, up it goes with the air. Temperature inversions occur when you get a stable layer of warm air that actually sits on top of cooler air. Now, why is this a problem? Well, warm air on top of cold air traps that cold air. Cold air normally like falls to earth, like it doesn't rise. So it's sitting right there like at ground level. So if there's pollution that's being created at ground level in this cold air, it's literally just going to sit there right on top of the community where, it's being made. Instead of rising maybe up into the prevailing winds and getting out of there, you're stuck with it. So this reverses the normal temperature decline with increasing height and prevents convection currents from dispersing pollutants. So like this is something that happens a lot in the Central Valley, especially in the winter months. You'll get a cloud layer on top of cold air that's at ground level, and it just traps all of our pollution. We get really, really bad air quality during the winter months as a result. This picture is just sort of meant to illustrate this idea. Normal conditions up top where pollution can be dispersed and blow out as warm air rises, right, and takes that pollution with it. And then down below, we've got that inversion where that cold air at ground level just, gets sandwiched in by a layer of hot air or warm air on top, and the pollution goes nowhere. Something else to consider when you think about pollution is that it can travel at really, really long ways. Fine aerosols can be carried great distances by the wind. We talked a little while ago about the fact in a different video that like the pollution produced here in the United States, like it goes all the way around the world in 2 weeks. A 3-kilometer toxic cloud covers India for most of the year. It covers like the entire like country of India, and it causes 2 million deaths per year. The cloud may also be disrupting monsoon rains, on which harvests in Southeast Asia depend. Like the particulate matter can have a massive impact on life. So, and it can move like huge distances. Don't forget that. Increasingly, like monitoring activity has begun to reveal that industrial contaminants in places usually considered amongst the cleanest in the world are no longer safe. We're starting to see industrial contaminants in Antarctica and the Arctic. There's no factories in Antarctica or the Arctic. How's it getting there? On the wind, right? So long-range transport of particulate matter can literally carry things thousands of miles and have an impact on communities thousands of miles away. I like to call it dumping on your neighbor. That's pretty much what you're doing. You put the pollution up in the air, thinking out of sight, out of mind, but it's got to come down somewhere. And I don't want to be the person that it comes down on. All right, from here we're going to look at stratospheric ozone depletion. So yeah, this is a form or a result of a form of pollution. Remember, ozone up high is good, ozone down low is bad. In 1985, we discovered that ozone levels over the South Pole were dropping rapidly, especially during the months of September and October. Basically what was going on is things like chlorofluorocarbons were entering our atmosphere. They were being used in refrigerants and propellants. And that stuff, once it gets up to altitude, attacks the ozone. This hole was reoccurring over the poles, well, and had been reoccurring since 1960. So it'd been around a while, just that like nobody noticed. And chlorofluorocarbons were the cause. So we banned chlorofluorocarbons, and I'll be honest with you, the hole is healing. It's getting better. But man, for a while, it was huge, and it was allowing excessive amounts of ultraviolet radiation to penetrate all the way to ground level, increasing the incidences of skin cancer, retinal damage, and even crop damage as a result. When you think about ozone at ground level, remember, is a pollutant. Remember, at altitude it's good, but at ground level it's bad. A 1% decrease in ozone at altitude could result in 1 million extra human skin cancers per year worldwide, and decreased agricultural production, right? We'll lose crops, we'll lose plankton in the ocean, and like disrupt food chains. This is just a picture of what the ozone hole used to look like, not still like this today. It has been healing. Circumpolar vortexes isolate Antarctic air, and this is what has allowed that ozone hole to form. These circumpolar vortexes, basically create ice crystals at high altitude and absorb ozone and chlorine molecules. When the sun returns in the spring, well, all those ice crystals melt. That liberates chlorine and destroys the ozone, and that chlorine can persist in the atmosphere for literally years. There was a time where we started to see a hole beginning to form over the Arctic, not nearly as big as the one in the Antarctic. The Montreal Protocol in 1987 is the law that basically phased out CFCs. So remember that. It was successful. CFCs were cut by 95% as a result of the Montreal Protocol. Now, keep in mind that this is something that the developed world adopted, but there are still places in this world that use chlorofluorocarbons, right? They didn't necessarily adopt the Montreal Protocol or agree to abide by it. So, although the developed world's doing better, there's still the potential for chlorofluorocarbons to enter the atmosphere. We're hopeful that because levels have been cut, that we can get our ozone pretty much back to normal by the year 2049. Okay? Now, the effects of pollution. So when you think about like why we care about all this, well, I'm just going to put it this way. The WHO, not the band, but the World Health Organization, estimates that each year 5 to 6 million people die prematurely from illnesses related to air pollution. Like, this is preventable. All we have to do is be more conscientious and more careful with what we're putting up into the air. The likelihood of suffering ill health is related to the intensity and the duration of your exposure to air pollution. You can have as much as a 5 to 10 year decrease in life expectancy just by moving to LA. Sorry, LA, but you got bad air. So there you go. As much as a 5 to 10 year decrease in life expectancy. Wow, right? Where does that come from? Well, all the things we talked about can lead to this, decreased life expectancy, whether we're talking about chemicals or something like this. PM 2.5. This is something that I like to really just sort of sit on when it comes to air pollution. These are particulates in the air that are 2.5 microns in diameter or smaller, and they can get into your lungs, deep into your lungs, and lead to heart attacks, asthma, lung cancer, abnormal fetal development. I mean, the list can go on and on. We have new rules to remove particulate matters from diesel engines and power plants, but at the end of the day, you could still get particulate matter from vehicular exhaust. You can get it from farmers plowing their fields. You can get particulate matter from ocean waves crashing on shore, because it's aerosols. You're still going to get this stuff. Most air pollutants are inhaled, which is why we have to be careful and concerned about this particulate matter. Some of our air pollution can actually be absorbed directly through the skin or even ingested in food or water, which is crazy to think about, but yeah, it happens. So here's some other things to think about with regard to human health effects. When you're taking quizzes and tests on this stuff, man, I don't want you to think that all air pollution causes cancer. It doesn't. It's going to irritate your lungs. It's going to make you feel lousy and do all kinds of other things before it ever leads to cancer, like bronchitis. Here's a great case in point. Bronchitis can be caused by air pollution, inhaling this particulate matter, whether it's dust and dirt particles, bacteria, viruses, fungus, whatever. Like, it can lead to inflammation in your airways. And as your airways become inflamed, mucus builds up, can create muscle spasms, constricting your airways. You're going to get an awful cough. Not a lot of fun. Bronchitis, if left untreated, can lead to emphysema, which is irreversible and chronic. And that emphysema can basically, evolve into what's called COPD, chronic obstructive, pulmonary disorder, or basically your lungs will become blocked to the point where you're sitting there inhaling and exhaling, but you're not really doing any gas exchange. In the U.S., half of all the lungs examined at autopsies show some sort of alveolar deterioration as a result of exposure to air pollution. And again, all of this stuff, it could be avoided if we're just careful about what we put in the air. Smoking is the most important air pollutant in the U.S. 400,000 die annually from diseases related to smoking. Basically, that's 20% of all mortality. The associated costs with smoking are estimated at $100 billion a year. Again, preventable, okay? Plants are even susceptible to pollution, not just people or animals. Chemical pollutants can directly damage plants or cause indirect damage by reducing yields. Certain environmental factors can even have synergistic effects, which means that the chemicals in the air can multiply their impact by being present together. Pollution levels too low to cause visible effects can actually still be damaging to plants. This will give you a case in point. This is a soybean plant that's damaged by sulfur. You can see, with the discoloration there, you're going to get a decrease in photosynthesis, a decrease in production for this plant. Acid deposition. We talked about acid rain in a previous video. You get your nitrogen oxides and your sulfur oxides up there in the atmosphere. They mix with water and it forms acid. Now, I'm not talking about the kind of acid that if the drop lands on you, it's going to eat your clothes or something. But in a cumulative effect, it can literally change the pH of our waterways. And normal rain is about a pH of 5.6. If we just drop the pH 0.6, 0.6 is all we've got to do. We will kill everything in the water, not just the big fish, but the little fish, the eggs, future generations, all of it, gone. We know this because, unfortunately, they've done experiments to prove it, where they've literally bombed rivers, lakes, and streams with acid and proved that, once you hit a pH of 5, nothing survives. It basically becomes as clear as a swimming pool, okay? So, acid deposition can have huge impacts up and down the food chain. It can damage forests. It can damage buildings and monuments, and it can even contribute to smog and haze. To give you some pictures to think about with regard to forest damage and buildings and monuments, let's check this out. This is a forest that's been damaged by acid deposition. The soil's been acidified to the point where the plants can no longer grow. And this is a monument, a statue that's attached to a building that's been hit with acid rain. The limestone's literally being dissolved over time by the rainwater that hits it, okay? So what do we do about it? Well, at the end of the day, we've got to control our pollution. And the best case scenario is for us to just not make it to begin with, right? reduce electricity consumption, insulate buildings so we don't need to like run, systems for heating and cooling and, use natural gas and electricity for that. Have some sort of energy saving transportation system, that is clean. Like these are things that we can do. We can try to remove particulate matter, but the technology is just not there to do it, on a grand scale yet. Best case scenario for particulate matter removal is to attack the source. So we'll go to a factory that maybe has a smokestack that's loaded with particulate matter and install something like electrostatic precipitator or a wet scrubber to try to get the particles out of the air, and save that from getting out into circulation. But once out in circulation, it's really hard to recapture this stuff. Oftentimes, you just have to wait for it to rain, and the rain just knocks it down to the ground. This is a picture of an electrostatic precipitator. Basically, the exhaust gas goes through some, ionized plates, and the particulate matter sticks to those plates. You collect that stuff, and it goes off to hazardous material disposal, right? All right, other air pollution controls. For sulfur, nitrogen oxides, and hydrocarbons. For sulfur, you can switch from soft coal that has high sulfur content to a low sulfur coal. You can, basically just avoid nitrogen oxides by using staged burners and selective catalysts in place of them. Hydrocarbon control, use closed systems to prevent the escape of fugitive emissions to prevent the hydrocarbons from escaping. Legislation. So there's some laws that you need to know. The Clean Air Acts of 1963 and 1970, followed by some amendments to that in 1990. In 1963, the Clean Air Act was first passed to kind of establish parameters for pollution control in the United States. It was amended 7 years later to identify specific pollutants that we were going to worry about and establish some ambient air quality standards that, outside of which we were not going to operate in. In 1990, we addressed acid rain, urban air pollution, toxic emissions, and ozone depletion. We've reviewed things several times over the past 30 years to try to make sure that, the air that is being breathed by us all is as clean as possible. And then, this thing came about, cap and trade programs. In 1990, cap and trade programs, were established to set maximum amounts for pollutants, but to let facilities facing costly cleanups pay others with lower costs to reduce emissions on their behalf. Now, I want you to just kind of understand what this means. So if I own a business that is polluting big time, and I get slapped with fines that say, you know what, you're a gross polluter, you got to stop. If my buddy has a business nearby and his business isn't hardly polluting at all, well, it's kind of like I can buy my buddy's pollution credits so that my business doesn't end up having to pay any fines, but I can still continue to go on polluting, right? That's how cap and trade works. We set a cap for how much pollution that we're going to allow, and then we allow businesses to kind of work out with one another how they're going to manage the amount of pollution that they're producing. So it permits local hotspots where high polluters can continue to pollute because they're paying somebody else somewhere else to reduce their pollution, that might be less expensive or maybe not even need to be like reduced at all. Not a big fan of cap and trade, but that's just me. All right. As far as trends in the U.S. is concerned, air pollution in the U.S. has improved. Our situation is getting better. It keeps getting better, and hopefully will continue to get better. Only pollutants that have not shown significant declines in the U.S. are the particulates and the nitrogen oxides. 80% of U.S. cities now meet the national ambient air quality standards, so that's fantastic. Unfortunately, we can't say the same thing for all countries across the globe. In developing Asia, Africa, and Americas, government intervention may be weak and regulations non-existent. So in some place like Mexico City, pollution levels often exceed the WHO recommended health standards. 350 days per year. Those like standards are basically like, out of compliance. The city's out of compliance. More than half the children have lead levels high enough to lower intelligence that are born in Mexico City. The incidences of asthma are off the charts. China's 400,000 factories have no air pollution controls, and the former Soviet Union has serious problems as well. There are some signs of progress. Sweden and West Germany have actually cut their sulfur emissions by 2/3 between 1970 and 1985. And Australia and Switzerland, they're even able to regulate motorcycle emissions. Even Delhi in India, which was once the world's most polluted city, has made huge strides, and the air is dramatically cleaner with sulfur dioxide levels reduced by 80% and carbon monoxide levels down 70%. So that's it, ladies and gents. That's the long, the short, and the in-between of air pollution. Indoor, outdoor air pollution, factors that affect it, and how it affects us. I hope you've learned a lot. I hope you appreciate that clear blue sky when you see it. I'm Mr. Kennedy, and I will see you next time.